Okay. Hello, everybody. My name is Martin Gutierrez, and I am a professor at Colorado School of Mines, also the director for the Center for Underground Transportation Infrastructure, which is funded by the U.S. Department of Transportation. I'm very thankful to the conference organizers for this opportunity to make a keynote lecture, and the title of which is Machine Learning in Underground Construction and Transportation. Let me give a very quick and very easy introduction on what machine learning is. Typically, when we have a computer modeling problem, it is the computer program itself that is the bottleneck. It's the one that takes time, it takes effort to establish. But what if we could let the data do the work instead? In other words, let's find a way for the data to speak for itself. That is to get the computers to program themselves, okay? Let the computers evolve the program. And that is what computer machine learning is. It's programming computers to optimize a performance criterion using example data or past experience. Okay. Here's the difference between traditional programming and machine learning. In traditional programming, we have a set of input data, and we have a built-in, already developed computer program to calculate the output. Now, an example of this is a finite element code, which is a very heavy program. That is why there are not many finite element programs available. Most of the time, we treat this as a black box. We don't really know how every detail that goes into this program. So we have input, a pre-built program, a pre-developed program, and an output. And again, this is the most difficult thing to build. In a machine learning environment, we have both the input and the output data, for example, from measurements. And we use computer or machine learning to try to look at patterns between the input and the output, and that becomes the program. So mathematically, this is the definition of machine learning. We have the output that we know of. We have the image picture, which is the input, and we have the prediction model or the function model. This is what we want to evolve. So there are two steps. One is training. We have a given set of data, x1 to y1, which involves both input and output. And by some means, by machine learning, we try to get an estimate of the prediction function by limiting the error between the real data and the predicted data, the real input or the real output, the differences between them to be as small as possible. Once we have the prediction function, we can then use it to the next stage, which is the testing stage we have now, where we have now a previously unseen set of text example, and we try to predict the results, okay? Okay, what are the steps in machine learning? It's pretty much established. There are essentially 5 steps. One is gather the data, which is actually the most time and resource intensive step. Okay, this is the one that takes more time. We need to clean the data, prepare it, because most of the time the data contains noise, errors, and anomalous data that we don't expect. Then these days, what we do is that we just select an appropriate machine learning technique or techniques. There are many such techniques that are already available. You can, of course, develop your own, but given the large number of availability of the techniques, most of the time we just choose the one appropriate for us. Then we have now the so-called subset of test data, training data, rather. So we train the ML using the set of data. And then we validate and improve the model using, again, the test set of data. And once we have the model fully developed, we deploy it and use it in our explanation. So this is a very simplified classification of machine learning algorithms. We have supervised or inductive learning, where our trained data includes also the results in the output, not just the input, but the output. In unsupervised learning, we do not have the desired output, and that is we want the machine learning to fully understand what's going on and even evolve and try to find what the desired outputs out. We can have a semi-supervised where only have a few of desired outputs. And then we have reinforcement learning, that is, we do an iterative process. We have a prediction and then see the difference between the prediction and the real data. And then if there's a significant difference, we go back, we learn from that first iteration, and we improve the machine learning iteratively until we have very good predictions. Okay, let me give you an example of supervision again. As I said, we have unsupervised, that is, does not include some data, and then supervised on one end. This is unsupervised. It's, for example, it's an image analysis problem. We have 3 sets of data: human beings, koalas, and cars. As you can see here in the unsupervised case, we can even have a mix of the data, a human being with a koala or a car with a koala. In the weakly supervised, we at least clean the data and take out the mix, the data that are mixed. We only have humans, koalas, and cars. And the fully supervised model, we give explicit descriptions of how to decide whether an image is human by telling that there will be eyes and nose and mouth. Same with koala, but the ears will be included with a bigger ear. And for a car, we use the doors as the criteria to decide that it's a car. Okay, another very simplified classification of machine learning problems and algorithms. We can have data that are discrete. These are real measurements with some distribution, or we could fit a continuous curve through the data. So this is continuous because it's given by a function. So we have supervised learning and unsupervised learning again, discrete data and continuous. If we have discrete data with supervised learning, the techniques that we deploy are classification or categorization. Unsupervised learning with discrete data, we could use clustering. We divide the data in different clusters. Continuous data, supervised learning regression, unsupervised learning, and continuous data dimensionality reduction. So this is a very simple classification of ML algorithms. What are the most used algorithms available these days? I believe these are the top 10, okay, that are widely available, widely used, and we know how they perform more or less, from linear regressions to naive Bayes, random forest, neural networks, and decision trees. So the challenge is to understand each of the algorithms that are available and to know which ones or combinations of different ones will apply to our application. This is the main challenge. By some estimates, there are now close to 200 algorithms available. And not only are they available, there are open source codes and libraries in Python or MATLAB that are widely available. So we just pick up the subroutines from these places. One of the most popular one is TensorFlow. Okay, why machine learning in underground construction? One is we have a lot of data that we gather during tunneling, particularly for TBM tunneling. The data is supposed to capture ground properties and response and structural response as well. The problem is the data are often nonlinear, noisy, and with high dimensionality. And they do represent physical mechanisms that are difficult to build a model from. Okay, the data should allow us to develop a data-driven modeling approach, and we can use that to optimally design tunnels using data and to look for patterns and develop predictive models in tunneling. Okay, I will present 3 problems to show you how we use machine learning. The 3 problems are predicting an tunnel ground collapse in rock, in the Jilin water conveyance tunnel in China. Third example is the predicting soil mixing and TBM clogging ahead of a tunnel in the Northgate Link Extension project in Seattle, Washington. And the third project is forecasting tunnel settlement and convergence in the Shanghai Metro Line #1. So the first problem, the Jilin water conveyance tunnel. It's a tunnel that's about 20 kilometers long, okay, made up of essentially 4 types of lithologies: limestone, diorite, tuff, and granite. Limestone is the main lithology. It's about 8 kilometers, followed by granite and tuff. There's only very little of the length of the tunnel that's in diorite. So the tunnel is excavated by TBM, 88% of which is TBM tunneling, and 12% is drill and blast tunneling. The tunnel is classified as rock type class 2 to class 5 in the Chinese hydraulic classification system. And these are the main lengths. Mostly the class type is type 3. Anchor pi compressive strength 38 to 95 MPa, and joint volume is 3.8 to 23 fractures per meter cube. Okay, the problem with this tunnel is that there have been a substantial 363 meters length of which collapse at different locations. It's a small fraction in general, but still it could be a potential problem. So most of the collapse are again in the limestone and the granite. The shortest collapse is only about 5 meters, and the longest is 53 meters. So there's 18 instances of tunnel collapse. And collapse simply means the disintegration of collapsing blocks from the excavated tunnel boundary due to the presence of weak or unstable rock caused by fault zones, karstic and karstic intrusion. Okay, this is the TBM use. This is the data about the TBM. It's an open mode grid per TBM, 8 meters in diameter. Okay, these are the different parts. The TBM was equipped with 199 sensors, okay, which are sampled with a frequency of 1 hertz. So it generated terabytes of volumes of data. In our machine learning, we used 70% of the data for training and 30% of the data for testing and validation. Okay, how do we build the classifiers? First of all, what is the problem? What is the objective? We want to develop a machine learning algorithm that can predict if the upcoming zone ahead of the tunnel will be normal, there is no collapse, or it will be collapsed as defined a while ago, or somewhere in between. Can there be a zone of influence that will warn of an upcoming and impending collapse? And that is the influence zone. So this is usually, these types of decisions and adjustments to the tunnel TBM operation are typically made by the TBM operator. What we want to do is to move from an experience base to a data-driven decision making to help the TBM operator. We chose these 3 classes of classifiers, MLP, SBM, and RF. Why did you choose it? Well, first we have to go back to the so-called no free lunch theorem by Wolpert in 1966. Essentially, it says is that we cannot pre-decide, we cannot choose an algorithm unless we test it first and see if it will work in our evaluation. We cannot prejudge an algorithm in terms of its performance. The only way to forward is to test it. So in other words, as the saying in English goes, the proof of the pudding is in the eating. So there's now, as I said, about 200 classifiers, but fortunately, Fernandez Delgado et al. In 2014 analyzed 179 classifiers and different data sets. And they concluded that the 3 that we selected here, these 3, perform better than most other classifiers. The best is actually RF, followed by SEM. In our case, this is true. I will show you RF and LP are the ones that perform, and actually SBM did not perform well. Okay. All right, so here's the setup of the machine learning problem. We have a TBM again, it's moving ahead, drilling, using the data from its 199 sensors, tell us if the upcoming zone will be normal, no collapse. Will it be a influence zone that will tell us next to it will be a collapse zones of certain length. The parameters that we use are the operational parameters for the TBM, torque, speed, advancing speed, and proportional force. And from which we develop performance parameters like the FPI, which is the force times the rotation, okay, divided by the thrust. Okay, we have the thrust times the rotation divided by the speed, rather, the speed and the energy. So using these 8 TBM parameters, we developed 3 classifiers, MLP, SBM, and random forest. And out of this data, and out of the thousands of data that we collected, we would like to predict whether the zone that is being evaluated is normal, collapse, or influenced. It's a typical appearance of the data for a 24-hour tunneling operation. As expected, there's ups and downs. So the downs are when the operation is shut down and stopped, for example, to remove clogging from the TBM and other things. After it died down, there is a rest period. And as you can see here, we have 4 segments of a typical cycle of up and down. We have the shutdown of the tunnel, we stop it. And then the TBM rotates freely without contacting the ground. And then the ascend operation when all the values are starting up. And then we have more or less a stable operation. What we do is the first thing is to pre-process the data, to clean the data. We don't compress, we use the data as they are, so we don't lose information. We remove the shutdown and ascending segments, and then this is now the more or less stable operation. As you can see, we get the mean of the parameters, and then we truncate the data. We take out data that are outside 3 or plus minus standard deviation because we consider them as noise or measurements error. Okay, we look at statistical distribution of which the parameter. The diagonal here shows you the distribution of each individual parameter. For example, the advance rate is normally distributed. Then we also look at the correlation between data. For example, the advance rate and the thrust, this one. Okay, that's the correlation between the 2 data. And see whether they're correlated and whether positively or negative correlation. This is just the reciprocal of, which one is this? AR times T, T times AR is just a reciprocal of this correlation. So this is for the normal zones, and this is for the collapse zones. And you can see that there's a lot more scatter in the cross correlation data for the collapse zones. Now, the reason for looking at cross correlation is that we might be able to reduce the number of parameters that are involved in the machine learning. Okay, so as I said, ML is one of those. It's nothing more than a multiple layer of neural network. Okay, with the input layer, with the hidden layer, and the output neurons. The input neurons, the hidden layers, and the output layers, and we go from one to another. So we use weighted sums to pass from the through an activation function to pass from the input to the output layer. Okay, we have an error here at the end, and to minimize the error, we take the derivative of the error function, which is a function of the weights, and then bring back the weights and improve the predictions. I'll show you a detail of this much later. Second one is the support vector machines, where we have sets of data. We try to find the boundary that separates the data, classify the data, or to cluster the data. Here is what we call the support vectors, are nothing more than the distance from the boundaries to the data. That's what we call support vectors. So we can have a hard margin or a soft margin, and we can use a hyperparameter C. If the data is nonlinear, in other words, the boundary is nonlinear, it's too carved, and so very complicated and difficult to separate the data, what we could do is use the so-called kernel trick, whereby we convert the data using a nonlinear function, okay, and bring it to higher dimension. For example, we have 2-dimensional here. The 3-dimensional X3 will be a functions of this data, and hopefully the function will give a clearer delineation of the data, and we can pass a hyperplane that separates the two data. Okay, and the third one is random forest. Random forest is just a collection of many trees. You have 3 decision trees here, for example, 1, 2, 3. You combine them together, and you become a random forest. It's very fast. It's robust against multicollinearity. This is why we, multicollinearity. This is why we look at the correlations between data a while ago. Okay, it's robust. If you look at the noises, okay, and outliers, it's less likely to overfit. In other words, it gives the predictions are much better than the performance of the fitting, and it has high accuracy. As I said, the collection of multiple decision trees, we average the prediction from each tree and do a major moting to get the final class. Uses CART. It uses looks for the best instead of the very best, so to increase its randomness and diversity. Another advantages. In doing a machine learning algorithm, it's important to decide what we call hyperparameters. These are parameters that are not the ones that you're learning for. This is not your data set. This is not the data that you're trying to learn from. They are parameters that control how the programs or the algorithms are being carried out. Okay, they're constant for each classification. So, for example, for the LMLP, we have used 3 layers. Okay, through neural layers. For activation, we use ReLU. For SBM, we have the hyperparameter, the one that's regularization hyperparameter to get a sub-boundary. And for the RF, these are is the data that we use. The third component, very important component of machine learning, is to decide how the machine learning performs. And for that, we need performance matrices. And one of the biggest, most useful way to judge the performance of machine learning is by the use of the so-called confusion matrix. Confusion matrix just simply shows the ways in which a classification model gets confused in its predictions. Okay, so we have 3 classes. Okay, influence zone, collapse, and normal. These are the true values. The rows are the true values, and the columns are the predicted values. Okay, depending on the relationship with the true classes and the predicted classes, we can have true positive, TP, whereby the machine learning algorithm shows a positive correlation between data, between input and output. Okay, so there's an agreement between input and output, and the results are predicted correctly by the machine learning algorithm. So we have a true positive. We can also predict a true negative, where there is correctly predicted, there is no relationship. The results are negative. There are no relationship between input and output. You can also have false positive and false negative. And C is the number of classes predicted. And from that, we can develop measures like accuracy, precision, which is a function of, again, of all these classifications. We can have precision as a micro average, recall, micro average recall, and the F1 score. Okay. If you look at the 3 procedures we have, the SBM, MLP, RF, we perform a so-called 10-fold cross-validation. This is nothing more subdividing the whole delta set, the complete delta set, into 10 bins, 10 parts, 10 sections, okay, 10 boxes. And we do simulations using 9 of the bins as training, and 1 of the bins, or 10% of the bin, as the test or validation. And we vary those, we do that 10 times. And then we look at the performance of each of the algorithms in terms of precision and recall. As you can see, the best performance is given by RF. a random forest with a recall precision of 95% or better and recall of 95% or better. The worst performer is the MLP, and you can see that the precision varies widely, for as low as 85% only, both for precision and recall, and it's not very stable. SBM comes in second. The performance is the precision is about 90% for both recall and precision. So these are the two, it seems, that are working well, SBM and RF, using a 10-fold cross-validation. This is another look at the performance matrices, the performance of the classifiers in terms of confusion matrices. You can see that SBM, RFP, all the three, the diagonal elements of the number of cases. For example, this one, normal, has 31,000 cases. 30,000 of those cases are positive, true positive. So they're all true positive, most of them. So in other words, in terms of the confusion matrix, all the different, the three different classifiers are working well. You can also look at the precision, recall, and F-word score and accuracy. And you can see here that, again, RF performs the best of the three classifiers. Now, it's important to look at the accuracy, the performance, in terms of both the training set and the test set. You can see here that in most cases, the performance metrics for the test set is lower than the training set, okay, except for MLP. There's a couple of instances here where the training set is, or rather the test set performs better than the test set. In that case, we have overfitting. The model has been overfitted. So not only is MLP the worst performer, it also overfits, because we get no overfitting if the performance for the test set is less than the training data. Okay, so I said the main challenge here is to see whether we can predict what we call an influence zone. Influence zone is simply the region, the length of the tunnel before and after the tunnel that will indicate that it is give indication that we are coming up with a collapse. If the collapse length is L, we tried four different lengths. We say that the influence line is the same as the length of the tunnel, down to 1/4. And if you look again at the performance of one of the methodology, the random forest, you can see that a length of 1/4 of the collapse zone gives the best performance matrix. In other words, it appears that the influential zone should be about 1/4 of the total length of the tunnel. So in terms of all these measures or metrics. And again, in this case, you see that performance in the training set is always better than the test set, so there's no overfitting. We look also at the confusion matrices, and you can see the highest predictions, positive, true positive predictions. The diagonal elements are highest when there's L over 4 compared to the other fractions of the length of the collapse zone. So these are some results. So we are able to classify as many of the collapse zones in terms of the different lithologies. Okay, so the blue is the green is normal, yellow is influence, and red data are the collapse zone. So it performs pretty well, I think, in predicting potential collapse. Okay, so what are the lessons that we have? It looks like we could develop ML that can be used by a TBM operator to control the TBM operation to a collapse-prone ground, okay? And also make a prediction of the anticipated intensity of the collapse. Okay, so we were able to prove that you can have an influence zone around the collapse zones. This influence zone can be used to predict oncoming collapse. Okay, we found that the length of this influence zone is 1/4 of the length of the collapse zones. We are able to predict, the existence of this influence zone to an accuracy of up to 97%. And of the three classifiers that we have, RF performed the best. Second sample is predicting soil mixing and TBA clouding ahead of a tunnel using ML. This is an air pressure balance machine, and it's important to anticipate what's ahead because one of the big problems is that the TBM can be clogging if we encounter a particular type of soil. Now, this problem is encountered in the Northgate Link Extension Project in Seattle, Washington. It's from University of Washington to Northgate Mall. Okay, so as I said, the EPBM tunneling is sensitive to the soil that is encountered ahead. And this is the stratigraphy, the soil profile, and we have mainly cohesive clays, till and till-like materials, cohesionless sand and gravel, and cohesionless silt and gravel. Okay. Depending on the composition of the soil ahead, depending on the plastic limit and the liquid limit, we can subdivide the soils into, depending on their composition, into strong clogging in this portion. Okay. We have a soft soil deposit, and you can get lumps, okay, hard portions, volumes of materials when you have a very large deposit. So mainly the liquid limit and plastic limit. So what we want to do is to predict the grain size distribution and the composition of the soil ahead using data from the TBM. There are 10 data, again, advance rate, thrust, torque, etc. We use these 10 data, and we use different types of classifications. These are the classifications that we're trying to predict, or we're also looking at the grain size distributions. The algorithms that we tried are random forest, ADABUS, MLP, SBM, and KNN. And here you can see that the machine learning algorithm is able to predict quite accurately the real gravel percent, sand percent, and fines percent, okay, from which again we can decide on the clogging potential. Okay, so it seems that the EPBM parameters are valid indicators of tunnel excavation phase properties to achieve efficient operation. We found that among the variables that we're looking for, the soil pressure ahead of the tunnel is the most important in predicting properties of the tunnel phase. Among the three algorithms, MLP detected the mixed soil clogging potential with the highest accuracy. For grain size distribution, RF is the best. For fines content prediction, RF and KNN are the better performers. Third example is settlement in the Shanghai Metro. You can see here the locations of the different tunnel of the different stations along the length and the soil profile, the different types of soil that are encountered. We also have here geotechnical data, the soil parameters that were surveyed. Okay, the problem here is, can we forecast using early measurement data? Can we forecast the settlement along the length of the tunnel? There were several measurements in three stations, train stations. Typical examples are here for about maybe 10 kilometers. Okay, there are also a few instances of convergence, horizontal convergence measurements along the tunnel at one station of the tunnel. So again, the problem is, can we predict using early measurements to predict the settlement and the convergence along the tunnel line using machine learning language? Here we just use the feed-forward neural network with backward propagation. These are the equations. You have here the input xi. We apply weights and biases to get the modified input parameter. We use a softmax activation function to get the output. We feed in the output and we get a new measurements of the input layer. And then the difference between the output and the input and the output layers, that is the error. We get the derivative with respect to the weighing function and get the new weight functions and then modify the hidden layer until we get good fit. And you can see here, using the first 2.4 years, this one, this is the fitting, this is the training set, 2.4. The total data set is, how much is that? Is I think it's 14 years. Okay, 14 years. Okay, so 2.4 years of training, 14 years of testing, and you can see that the settlement are predicted quite accurately. There's some differences here, a little bit, but it's still the performance very good. Same with the convergence at the 3 stations. The green points are the actual data. The triangular points are the predictions, and the errors between prediction and actual data is less than 20% in most instances. So the predictions are quite. In terms of long-term settlement and convergence, we are able to predict with accuracy of R² of 97% and R 97 to 94%, while the normalized root mean square of errors is this value. So again, we are predicted to predict from 2.4 years of training to 14 years ahead. So let me summarize everything that I have here. Okay, ML, machine learning, can significantly improve the analysis and design of tunnels due to the enormous amount of real-time monitoring data that we gather and we generate. The problem is the data are nonlinear, noisy, and with high dimensionality. So to make sense out of the data, we can either develop complicated models, which is impossible for TVM tunneling. And we could use machine learning to identify hidden patterns for data-driven predictive modeling. Showed you 3 examples. Okay, as I said, there's a multitude of algorithms that are available. Okay, so many. Okay, and the task is to find the best one for your use. The problem is the no pre-lunch theorem. We cannot pick and choose and say this is what we want without actually going through the process of machine learning. But according to literature review, studies done before, MLP, SBC, and RF seems to be the best. And indeed, we found them to be quite good in application. In fact, the best may be RF and SCB in that area. And don't forget that essential components of machine learning are the data processing and criteria, performance criteria to judge the performance of the models. So of the algorithms. With that, before I end, I want to thank my PhD students, Sharmin Sarna and Menki Su. Menki is visiting student from Tongji University. The results here are mainly from their work, and also, of course, the support of the U.S. Department of Transportation to our center. Thank you very much for listening. Again, I appreciate the opportunity to present. And if there's time, I'll be happy to answer any questions that you might have. Thank you and goodbye.